Hey, what's going on, everyone? It's Sean from All Things EV, and this is an in-depth recap of Tesla's Battery Day that just took place yesterday. I'm fortunate enough to be able to have a really special guest, a good friend, Ravi Kempaiah. He's a PhD candidate at the University of Illinois for mechanical engineering. He's a really, really smart guy and understands the technical aspects of batteries. And that's why I brought him on to help us sort of make sense of a lot of the stuff that Tesla talked about. Ravi, welcome back to the channel.
Sean, thank you so much. We go way back, maybe 18 months when we started the whole thing, and we started learning about Maxwell. We started learning about different solid state chemistry last time. Thanks for having me on. It's a real pleasure.
Absolutely. I'm incredibly excited to dive into this, and I'm glad that it worked out with our schedules. So I'd love to get your take on this. I'll just give mine because you'll probably have a little bit more of an in-depth take, but it was really, really encouraging for me to see all of these acquisitions that Tesla made over the period of the last 12, 24 months. It was really encouraging to see them implement them into different parts of this presentation. And if you've been following Tesla for a little while, you probably picked out on exactly which parts fit into this master plan to reduce the cost of batteries. So I was really excited to see that. It was highly anticipated from that perspective. There were some surprises in terms of cost reduction. It exceeded my expectations in cost of the battery pack per kilowatt hour. And they also revealed some other interesting things that I had some senses about. We'll probably get into that a little bit more in detail in terms of who they're going to be partnering with to execute on these items. But I'd love to get your take on this. What did you think as you were watching this, Ravi? And over the last 24 hours, what has gone through your mind?
Well, the presentation was awesome. There was so much to absorb. They covered so much material, and just the scale of problem they're trying to attack. They're talking about terawatt hours. They say tera is the new giga, and that scale is absolutely overwhelming. And the kind of engineering they're trying to do, the kind of problems they're trying to attack, at the end of all of it, they said they can reduce the cost of battery pack at the pack level by 56%, and that was extremely impressive. Overall, what they're doing is just amazing. First principles thinking, attacking every problem in the supply chain, the chemistry, the manufacturing. I thought it was very inspiring.
Now, this is not an overnight transition for Tesla. This is a 10-year plan, and we should start to see some of these changes in the next, let's say, 12 months. So there's a lot to cover. I want to let you sort of drive this a little bit, and much like what we've done with previous conversations, I'll jump in and maybe ask questions that I think people who are watching might have, and I'll also, if I've got some questions or some thoughts to add, I'll make sure and find an appropriate place to interject and add those. So why don't you go ahead and dive in, because you've got some slides that you prepared. We'll make sure and integrate these into the video as people are watching so they can enjoy them as well.
Sure. So let's jump into the first slide here. And so they talked about reducing the cost, which is the biggest driver for adoption of electric vehicles. It's just 1%, less than 1% of the whole fleet. And if they want to increase that number to 20 million cars, which they're saying by 2030 they want to have 20 million cars, they are going to bring the cost down, and they did in a very strategic way. So the first slide we are looking at is the cell design, and I thought it was the most amazing, very clever design. This has been, cylindrical cells have been around for a couple of decades, and now they're fundamentally changing the way cylindrical cells are built. And they did go from 1865 to 2170, and they did see 50% increase in energy. We need to make sure that this is the energy, not the energy density, because energy density would be just quite close. So going from 18650 to 2170, they only saw maybe 2 to 3% increase in energy density, but they could pack a lot more energy into the into the cell. But going from 2170 to 4680, now that's a huge leap. And question is, can we see 5% energy density increase, not energy, but 5% energy density? So I'm thinking the state-of-the-art Model 3 was 251 watt-hour per kilogram, because they didn't mention this number. So are we able to see 265, 270 watt-hour per kilogram, maybe 275? That's something I want to explore with you in this talk, in this discussion. So moving on, if we go to the next slide. So the cell energy density is not just dependent on cell design, which they did change. They did change the tab design, they changed the current collector design, the cap design, all of that, but there's still a lot more, separator, electrodes, materials. Within electrodes, the chemistry, the loading density, and then porosity, all of that matters a lot. So we'll get to that a little later. And I think the fundamental limit is still the chemistry. That's the bottom of the pyramid. And then you have manufacturing, you have cell design, other stuff. But the fundament, it's still limited by the chemistry. So they did change some of the chemistry in the anode side, going to silicon, which I thought was quite amazing as well. Quite ambitious, actually. So going next. So, I thought if we change, one interesting thing Drew said is that anybody can change the cell form factor from 21 to 46, and then Elon interjected and said, any fool can change the form factor, but we are not just any fool. And I think there's a lot of stuff that goes into building this 4680, and I want to just touch on a couple of things. One is the cell resistance itself. When they designed, this is from a really nice paper in the Journal of Electrochemical Society, they compared 18650 versus 21700. And when they changed the cell form factor from 18650 to 21700, the cell resistance, what we see here, that goes down from, for 18650, you can anywhere from 20 to 35 milliohms per cell, and that goes to 10 to 15. That's a huge change. And I think as a result, they could get a lot more power density out of it. And that's why I believe Model 3 can be charged at a much higher. And not only that, of course, the power electronics, they went to silicon carbide power electronics. That did change a lot of things in terms of power density. Now, going from 21700 to 4680, I think that's going to be in the range of 3 to 4, maybe 2 to 3 milliohms per cell. Because they're talking about, if we go back to this, they're talking about 6 times power. That means that there has to be a way to extract a lot more power out of it. That means the cell resistance has to go down significantly, 2 to 3. Now it's in the range of large pouch cells, or even, some of these large pouch cells have very low resistance. And I think this is going beyond all of those, and it'll be extremely low resistance. So one of the point they discussed is that the jelly roll, right? Now the jelly roll, that's fundamental for 18650 or 21700. And actually I did make some contraptions here. So if you look at it, so imagine this is 18650, and then this is 2170. This one is 2170, and this one is 4680, the new the big cell, right? So if you look at this jelly roll, what they presented yesterday, and they say the jelly roll in 2170 is more than a meter. So this is 2170, right? This is the current 2170. Imagine this aluminum foil is a cell can, and we open it up. Okay, we completely dismantle it, and then what do we find? We open it up, and then we find there's a tab. There's a tab here, and one other tab had actually disappeared, but there's a tab here, and you begin to roll, this is the jelly roll, and then suddenly you see, okay, we have to unwind 1 meter, and then you find a small tab, and this is the tab design that we have right now, but that's 2170 right now. Let's go to this big 4680 cell. Okay, let me remove this rubber band here. Let's remove the top cap here. We remove the top cap, and then we start unwinding the cell structure itself. As we slowly unwind the structure, we take it apart, and then we see the jelly roll, which is basically the sandwich of cathode, anode, and separator. So as we take it apart, you will see it's got like, sorry, I should probably like, so what we see here is every section, every segment has a in the patent, let's go to the patent in this design. So this is the 4680, what we see on the screen. That's a 4680 cell. And if you look at the bottom, the number 118 is the key for making this 4680 happen. And that actually, I did try to put it in the form of like sticky, sticky notes. So what you see in the bottom here is like a shingled spiral, right? And the bottom cap has something like this grooves. So if you look at the screen here, they manufacture the 4680 in such a way that the bottom number 118 has a conductive coating. So so in the case of 2170, they have to stop every 1 meter. They have to stop, put a tab. But in this case, they can roll it continuously, so there's no stoppage, and then it's quite fast. And also what happens is every segment, like it's the whole bunch, has outlets for connection to current collectors, and the bottom plate has grooves like this. And if you look at the screen, so that's what they say. This is the design they shared, and the copper shingled spiral can be, we can compare it to this. So basically there are hundreds of outlets that connect to the current collector bottom plate. I believe the current collector is already there, but this is the final lead that takes all of that and then transport. This is the negative part of it, right? So the plus, the upper one is positive, and then this is the anode side. So what they're trying to do is, all the grooves that you see in the picture here, figure 6b, the jelly rolls, each layer leads to a single, it's not single, but it's kind of a extra material that acts like a pathway for these electrons. So basically, that's what I was trying to explain here in this, right? If you open it up, if you open the jelly roll here, now I don't have to travel 1 meter every single between every segment, probably that's exactly what Drew was saying. Now we go from, instead of the pathway being 250 millimeter, it is 50 millimeter. So they're reducing it by 1/5. And what they're doing is, every segment has this structure here, the sticky tape that leads to the final current collector basin or the bottom cap. So instead of the electron, previously, if there was electron here, it had to travel all the way down to the tap and then go out. That would create like a bottleneck. But here, electron, it can go here, it can go here, it can go here, it can go here. And then throughout the jelly roll, we have hundreds of structures like this. So electrons have so much more conductive pathways, it makes a whole lot of difference. And the bottom structure, the grooves that I'm trying to represent it here, right? The small grooves. So each group can take in all the electrons coming out of the anode, and then as a result, what we see is 6 times increase in power density, and then low resistance, very low resistance. I believe they will be, so this is exactly what I was trying to do. If you look at figure 10D, I was trying to replicate figure 10D here. This is the bottom plate of the cell, and then each one of the structure, like a triangular structure, is conductive. It takes, so the patent says it could be in a triangular protrusion or a circular spiral, many different designs. All of this will increase the electrical pathway and therefore make a lot of difference for the power density. So that's exactly what is happening. 250 millimeter versus 250 millimeter path length and fewer parts. So this is another interesting stuff that I thought is worth mentioning.
It seems like a lot of automotive companies, traditional automotive companies, are utilizing pouch style cells, and someone who might be observing from a very surface level might think that the cylindrical cells are sort of old technology and automotive is sort of moving to a pouch style cell. Tesla seems to be quadrupling down with the cylindrical cell and taking it several steps further with this new patent that you've just done a really good job at simplifying with toilet paper and paper towels and sticky notes. So has this sort of innovation and forward thinking with a cylindrical cell been done before by some of these larger battery producers like CATL and Panasonic and LG Chem? And if this is such a great idea from Tesla, why didn't these larger companies think of that?
You know, that's exactly, I think there's a lot more that goes into it. Elon was mentioning it looks simple, but once we figure out in hindsight everything is simple, but you know, actually realizing it in scale is quite complex. I think there's a lot more that goes into it, rather than not just the pathways and other stuff, but the engineering of the whole cell. Not only that, the positive terminal that they mentioned, that's a lot more intricate details. For example, if we go back to this patent here, the bottom cup has lots of terminals, but the top one has still a couple of tabs, right? And if you look at this figure 3A, they are doing something interesting, very interesting here, because if you look at the number on the figure 3A, 114 is okay. That's a conductive strip at the bottom of the jelly roll. But what about 118 and then 114, right? And so that, okay, maybe 1110 is they're sandwiching different layers. That's fine. But I think engineering all of that takes some ingenuity, and I believe this leads to a cascading effect in the industry where more companies will try to adopt this kind of a design in whether it is cylindrical or pouch design, trying to make the tabs go away.
It seems incredibly innovative, and you know, if we were fly on the wall with some of these conversations that Tesla was having before they made this announcement, you know, they're trying to figure out how to reduce the cost and increase volume of production of batteries. Why could they not just have gone to Panasonic and said, we want to do this? Why bring this in-house and maybe have to invest significant capital into building their own cells, their own facility? Why not just ask Panasonic to do it?
Well, my understanding is that some of these companies have huge inertia. A company like Tesla moves at a really rapid pace, and they have the means and the end goal. They want to put all of this into the electric cars. So other companies have a lot of inertia to get to that kind of pace. And why didn't they? I think there's a lot more that goes in, as we said, they're introducing dry cell technology into both the positive electrode material and perhaps into the negative anode side as well, that in the future. And then they're introducing silicon instead of graphite. So these are completely radical innovations. And the cell design itself, it's funny and it looks simple, but why didn't others think of it? I don't know. But I think the engineering would take quite a lot of capital, tooling cost. And why would, if Panasonic is making money, quite a lot of money selling 18650 and 21700, why would they drastically change and invest probably like $100 million or more, even more, into this if nobody is, first of all, if they do this, they have to convince the other parties that, hey, this is better, and then do all the R&D, and then the tooling cost, assembly line, everything, whereas Tesla can absorb that and probably take it much, integrate vertically without depending on somebody else. So that's my understanding. But, as Elon said, everything looks easy after they discovered it, but in hindsight, it looks easy, but doing it in reality, quite challenging, actually.
I'm incredibly excited. This is going to be really exciting for them to actually execute on. It seems very promising, and as you're explaining this, it just seems very innovative and forward-thinking, and we're going to get into some of the other aspects of what they're doing to reduce costs, but this seems like a really significant one. So I'm just going to kick it back over to you and let you run with this.
Sure. One of the other thing, the implication of this big battery is that reduced cell resistance, and not only that, they're bringing in structural changes to the pack itself, and I think all of that what lends to extreme fast charging. This was an interesting graph in the presentation. They said when they hit that sweet spot of 46 millimeter width or diameter, they were able to reduce the charging time from tabs. It was quite high. The supercharging time went almost flat. So what I'm thinking is this would lead to mega chargers in being reality. If you want to charge a semi truck, so this is what Elon said, right? Elon in 2017, when they released the truck, they said 400 miles of range in 30 minutes and guarantee low electricity rates for Tesla mega chargers worldwide. And if you want to see this kind of trucks moving around, they need to have extreme fast charging, that we are talking about 400 miles in 30 minutes. That would necessitate close to 1.5 megawatt hour charging for semi or Cybertruck. And how can they do even Model 3 is hitting probably like 150, 200 now, right? I'm not sure if they're doing close to 350. Do you think it's Model 3 hits 350 now?
It's at 250.
250, right? Now 250 at that level, 250 it would take like 4 to 5 hours to charge, even constant 250 to charge a semi. Semi is expected to have 1 megawatt hour pack, so that would take like 4 to 5 hours. But if they bump the charging rate to 1600 kilowatt hour or 1.6 megawatt hour, then they could probably do it in 30 minutes. And how can we get 1.6 megawatt hours with the previous cell design? I guess this is what is needed. The big cell design, decrease the path length from 250 to 50 millimeter, lower cost of manufacturing, extremely low cell resistance. Now we are talking about 1.6 megawatt hour charging. So that's my understanding. Well, at least that's what I would expect. If semi has to make sense, they need this kind of cell design, extreme fast charging. What do you think, Sean?
Maybe the one question that does come to mind is, okay, these vehicles are going to be able to take a lot of high power. How are they going to generate this energy? Elon has talked about renewables and powering vehicles with sunshine, with solar panels. How are they going to generate this much power if they're going to be generating from renewables? That may be a whole nother topic of conversation, but these vehicles are going to be very hungry because they're going to be taking very fast charges, faster than what we know right now. So Maybe no one knows the answer, but these are some of the things that come to mind.
Yeah, from what I understand, for semis, they will have hubs within like every 400 miles, and these hubs would have installed mega chargers with few megawatt hours of capacity, or not megawatt, maybe like 100 giga. No, that's 100 giga is still too high, but let's say 10. Maybe 1 to 10 gigawatts of power, stationary power, combined with solar. So when this truck comes in, charge right away, and then the battery pack in the backside can get recharged over time. Anyway, that's just my assumption. So another thing, we talked. This is something we discussed back in May 2019. The role of Right, a lot has changed since then, and looks like they're making a good headway into that as well. So they said Maxwell dry electrode stuff is on revision number 4 as of now, the machine, and they still need a lot of work to make it work. And I guess this will be one of the limiting points to get this dry battery electrode stuff working at scale, and then integrate that into this 4680 form factor, but making sure this dry electrode stuff has the cycle life, because what Elon mentioned is that it was still proof of concept, and they're now revision number 4. They still expect another 3 to 4 revisions, so we still have another 1.5 years to go to actually realize the benefits of dry battery electrode for the positive electrode, and perhaps even for the negative electrode materials. And then most importantly, if you look at this chart, the dry battery electrode stuff comes here. That means the biggest improvement is 10 times reduction in storage, the floor space, the equipment cost, and also the time is like 1/10. That makes a massive difference right here, just in this stuff here. And then they remove the tabs. You see just one tab here, and in the new cell there won't be any tabs. So combined with the tabless design and DBE, we can expect significant improvement in the power density and energy density. Now, this is common, the bottom insulator, the bottom cap, top cap. This part is common for whether it is 2170 or 4680. But what was also another interesting stuff is they mentioned the formation. They were able to reduce the formation cost, equipment cost by 86% and the footprint by 75%. I believe they were able to do this using their experience, power electronics experience, designing the power wall, the battery packs for the cars. So they have done amazing structures. If you look at these formation cells, booths, and this is the close-up of the booth. This is like 4680 cells going inside. Formation stuff basically happens here, right after you put, you fill this electrolyte, you crimp the cell is ready, and then you have to charge it. You have to charge it and make sure it takes a couple of days. And what it does is the positive electrode, the lithium goes from they charge it, and during that time, lithium ion goes from whether it is NMC or NCA to the graphite or silicon, and when in this process, a thin layer of electrolyte interface, it's called solid electrolyte interface, forms on the negative electrode, which is graphite or silicon in their case. This process takes a couple of days. Maybe they were able to accelerate it, and they know exactly at what temperature, at what voltage, and what conditions we can do this quickly. And having booths like this, thousands of cells at a time, they were able to increase they were able to reduce the formation investment significantly. I thought that was quite impressive as well. Now moving on. So what does it mean? Cheaper and more efficient 4680 cells. So this is from a great paper where they compare 18650 and 21700. Now the amount of anode and cathode material is still going to be same. It is the same for 4680 as well. But in our case, going from 18650 to 2170, they saw 33% reduction in cell housings, the cell outer shell, the top cap, bottom cap, all of that. Now, going from 2170 to 4680, I'm expecting like 50 to 60% less cell housings and caps. And another thing they mentioned is that one assembly line would lead to 7 times output, and it would be able to produce 20 gigawatt hours. That's amazing. So the coating, drying, calendaring is greatly reduced because of the dry battery electrode stuff. Winding is much faster because there are not many tabs. It's a continuous process, and then electrode filling happens. So going from 18650 to 2170, 33% lesser. Now from 2170 to 4680, we can see at least 30 to 40% faster, and the formation is quicker, and the pack itself. Now, if you look at the pack, for a certain amount of energy, you need 24 cells of 18650, only 16 cells of 21700. Now I'm guessing if everything is as per the design, for example, the volume of 18650 around 65 centimeter cube, 2170 97 centimeter cube. Now going to 4680, it's almost 530 centimeter cube. So I'm thinking they just need 4. If you look at they just need 4 cells instead of 16. So that means drastic reduction in welding, and welding. The pack would need they do ultrasonic welding, right? And the amount of times the machine has to stop and go, that will be reduced. The amount of material needed to weld, the strips needed to weld, would be reduced. And they just need to weld 4 cells instead of 24 in the case of Model S. Imagine the Model S has 18650, 24 cells for a certain amount of energy. It's just 4 cells if we used 4680 in the Cybertruck or the Semi. I think that changes.
You estimate that they're using 50 to 60% fewer cell housings and caps,
right,
with this new cell, this new form factor.
That's what that's just a rough back of the envelope guess.
It's pretty remarkable. It should take them less time to produce each pack, correct?
Exactly, because now they don't have to fill as many. See, in the case of 18650, they had to fill 24 cells, electrolyte filling, formation, winding, but they just have to do it for 4 cells, and the machine doesn't have to stop for tabs, installing the tabs on each of those jelly rolls. So only 4 cells. So the time reduction is massive, and the material reduction is massive. The time and the cost, equipment cost is less, and they're combining the dry battery electrode, so the floor space is less. I mean, no wonder they're able to do 150 gigawatt hours in a given space right now, and that would go to 1 terawatt hour with less footprint. How are they able to do that? I mean, the only way I can think of is you need less housing and cabs. There's this part doesn't, you would have 10 times reduction in the floor space because you reduce all the large ovens, waiting time, the solvent drying process, all of that is reduced here. And then you need to wind only 4 cells instead of 18 or 24 or 16, and the formation is quicker. So combining all of that, now you can produce 1 terawatt hours capacity in a floor space that would only produce 150 right now. So that's like amazing combination of manufacturing and cell design and all of this cumulative effects. It reminds me of Team Sky, British cycling team Team Sky introduced this marginal gains rule, and they were able to win Tour de France, Olympic gold medals, because they would increase 1% increase in every aspect, better clothing, better tires, better grips, better lotion, everything. So I think Tesla is doing something like that. Quicker winding, no coating and drying, fewer number of cell caps, fewer welding, the amount of material needed to weld, and then it's just 4. So combining all of that, it leads to massive improvement, and it is cheaper and more efficient. That's amazing.
This is really fascinating. Are you going to touch on how this pack could potentially need to manage the heat in that pack, because you've got these larger cells, and I would imagine that you'd have a reworked system of battery management and thermal heat.
This is exactly what I was trying to allude. So the discharge energy is much this is discharge energy per watt hour, and the cell resistance. So let's see. 21700, the cell resistance is low and the discharge energy is much higher if you look at it. Now, the 4680, the data point would be so far away, it will be something like 30 or something here if you extend this graph, and then the resistance will be so much lesser. So what I'm thinking is, it wouldn't take massive reworking of the BMS and the cooling architecture, because you just need to cool. If the cell doesn't get too hot in the inside, then you just can cool the outside. You don't need to worry about heating up the inside. And if we had this kind of a design, right, the previous 18650 design where there was only one tab, and the electron has to travel like 50 to 1 meter to get to the current collector. But in this case, the inner side, if you look at the graph, the inner semi-concentric circles doesn't heat up. If it doesn't heat up, maybe you just can get away with cooling the outer surface. So that's what I'm guessing. If they have to bring the cost down, if the cost of BMS and the cooling architecture and all of that increases, well, that may bring the benefit down a little bit. So that's my hunch, but I don't know the next new cooling architecture. It'll be fascinating to see how much better it would be. All right, so moving on. So this was an interesting paper, battery materials for low-cost electric transportation. What they're expecting is, I did some calculation here. So, so they are also thinking about not only the cell design, they're also thinking about the cell materials, right? The cell materials, for example, if you want to produce 1 gigawatt hours of energy in NCA, in the form of NCA, you need 695 tons of nickel and then 131 tons of cobalt. 131 ton of cobalt would cost you $4.7 million. Okay, now they're expecting by 2030 there will be massive shortage of cobalt shortage, and then there'll be nickel shortage as well. Class 1 nickel is expensive. So Tesla has to work on improving the supply chain, and Elon was saying, hey, if you can mine nickel in an environmentally efficient way, we'll give you a giant contract. So they were able to eliminate cobalt. We will get to that in a second, and that gives you, just for 1 gigawatt hour, the company will save $4.7 million because they eliminate cobalt, and I think that's fascinating. But there's another challenge with high nickel content. Professor Jeff Don has done amazing research into this, the benefits and how to reduce cobalt and what happens if you increase nickel. We'll get to that in a few slides. But Tesla is approaching the problem from every angle. So the summary is that they want to get to 1 terawatt hour in a very small footprint and do it efficiently and faster. So what do you think, Sean?
I'm just wondering how this seems such a grand challenge to solve. I'm just thinking, when did they start this? This was not something that they just thought about 12 to 24 months ago. They probably have been working on this for years. it seems like such a grand undertaking to attack this from every different angle and try and improve this in every way possible.
Yeah, the scale they're talking about is just unbelievable. I think sometimes I think it's a little bit optimistic. It's good. The challenges they're going to run into is getting the DB work efficiently and improving the supply chain where they have enough. If you want to produce 1 terawatt or even 200 gigawatt hours, you need to have the supply chain. Otherwise, who's going to produce nickel? Who is going to give you all the other material? So those will be the bottlenecks, and there will be another bottleneck, which is the anode itself, anode and the cathode, the chemistry, fundamental chemistry. So it's interesting. You have interviewed. You were thinking of interviewing some people with lithium ion, right, in Colorado. I think their work is fundamental to Tesla's anode design. So let's get to the cathode side first. The cathode side, they're going to go with they're going to go with diversified cathode approach, right? The iron-based long cycle life. Have you heard of BYD's new design? And BYD and then CATL are coming up with new LFP batteries. They're approaching close to 200 watt-hour per kilogram. That is amazing. They're at 180 now. They say probably by next year they will hit 200 watt-hour per kilogram. That's very close to what you have with NC or NMC. Once they hit 200, that's an amazing number. So low cost Model 3 and other stuff, stationary storage, iron-based. But the diversified cathode, it's interesting. They have eliminated aluminum and cobalt, and they're going with nickel and manganese. Some of this work is the contribution from Professor Jeff Down's group at Dalhousie, and then high nickel content. Also, they've done amazing work into high nickel content. So I'm thinking high nickel content would include novel coatings and dopants. This looks like single crystal to me. Even though there are lots of grains here, these grains could be bigger. In polycrystalline, the grain size is much smaller, whereas in the single crystal, you will still have lots of grains, but these grains will be much, much larger, like in the micron scale. So what we are seeing here is that as you increase the nickel content, you will hit a limit somewhere around close to 0.758. I forgot to include an image. Let me quickly show the image that I was talking about. Okay, can you see? So they were talking about, Drew was talking about, the cathode is like a bookshelf, and this has to be stable when you cycle for hundreds of thousands of times, and they can get away by removing cobalt. To get the stable cathode where the bookshelf retains structure for thousands of cycles, there is a challenge, and this is something they have to overcome. As you increase the nickel content beyond a certain point, this bookshelf that we were talking about changes this unit cell. Imagine if this is the unit cell of the cathode electrode material. That changes the volume. Volume changes happen at that level, high nickel content. And the Professor Don used to call this unavoidable challenge for high nickel content. So this will be a challenge that Tesla has to overcome and still retain very high cycle life when you cross like really 811. Now going from NMC 5322, they'll go to 622 and then go to 811 eventually, and then even higher, maybe 9.5, 95.5, something like that. At that point, the bookshelf becomes a little bit crumbling. And how are they going to manage that and still retain cycle life? And if you have to get a million miles, you're talking about 2,000, 3,000 cycles. Can they retain 2,000, 3,000 cycles at high nickel content? That's a challenge they have to overcome. So that's why Elon said probably it's more like 2 to 3 years down the line before it gets into high volume production, right? And now let's go to the next one. So this was a Milestone paper that was published last year, is cobalt really needed? And this was published in the Journal of Electrochemical Society. What we see here is lithium nickel oxide, lithium nickel aluminum oxide, lithium nickel manganese oxide. All of them have very high nickel content. Okay, in this case, the right one has cobalt and the leftmost has no cobalt, just pure nickel. And if you have pure nickel, you will see these spikes. These spikes are detrimental for the stability of the cathode and long cycle life, that you need to reduce these peaks. All right, you don't see much peaks if you have nickel and aluminum. Nickel and manganese, there's not much many peaks at all. And nickel and magnesium, that's fine. And nickel and cobalt, you still have a peak, and that's not good. So we can neglect this one, and they will work with some of these. I believe this nickel and magnesium will. This is what they were talking in the previous slide. Nickel and manganese. Nickel and manganese. This one, with the right kind of electrolyte, right kind of stoichiometry of the positive electrode, right kind of anode, graphite anode, that'll be crucial. And that's going to the mid-size segment. And the high cycle life, high energy for semi and Cybertruck, they may deal with nickel and aluminum or nickel and manganese. I'm not sure yet, but they may have worked out that detail already. So another important aspect is the anode. Everybody's using graphite, synthetic graphite and natural graphite, but Tesla is going away, and they're going to go to silicon. And I think this is amazing, but at the same time they will have a little bit of challenging time to get all of this done, because I'm going to get to that in a second. Another really fascinating thing for me and for everybody was that the anode design they showcased yesterday, it's like $1.2 per kilowatt hour. That's like amazing compared to everything else. If you look at what is in Tesla right now, SiOX, they do have silicon oxide in the graphite right now, and that's costing them around $6. And silicon structured in graphite, there's another category that's about $10 per kilowatt hour. Now they're almost reducing it by 10 times. That's amazing. And so I was able to go search and read a little bit more on this. But I guess this will be one of the bottlenecks for their volume production, because believe me, the work done at Stanford, Professor E. Choi is one of the respected scientists, okay, and he has been working on silicon stuff for the last 15 years. But the biggest problem is, as you know, silicon, when you put lithium, it expands and it breaks because it expands 4 times. But on the flip side, you get amazing capacity. It goes from 370 for graphite to almost 10 times, more than 10 times. So back in 2008, they started with nanowire architecture, and then core shell hollow, double wall hollow, all of these. But the problem with all of these is that you can't scale these technologies really fast and to really high quantity at desired economic levels, like $100 per kilowatt hour for the whole pack. That's just impossible, because the manufacturing of all these anode materials cost a lot more. And then they kept improving. They did self-healing, so if it expands and breaks, the polymer coating on the outside keeps it together. And they did design pomegranates-like structures, non-filling coating, finally microsilicon graphene cage using graphene. But all of this, this is quite hard to scale up. And the way Tesla is, I think, trying to attack is through the technology acquisition of Sil-Ion, the company that you and I have discussed in the past. So if you look at their approach, they take metallurgical silicon and they pulverize it to micron scale particles. Micron scale particles get stabilized, they get surface treated using some kind of polymeric and ion conducting polymers. It's an elastic polymer. I believe it is conductive polyacrylamide nitrile, PCPAN. And even upon charging, it maintains robust network. So there's always, it doesn't lose active mass, and there's always capacity to store lithium. Even if it breaks, it doesn't lose. What happens is once it breaks apart, then the solid electrolyte interface covers these structures massively, and the capacity starts going down pretty quick. But they're going to use silicon. So the question is, how much silicon are they going to use? This is something they didn't discuss. There are a couple of things they didn't discuss. So they did say 56% in reduction of cost. So are they going from $125 per kilowatt hour to $65 per kilowatt hour? That is something they didn't explain. And silicon is one other thing. How much silicon are they going to put into the anode? Is it going to be pure silicon? Is it going to be some graphite and some silicon? Because as you change the chemistry, you need to optimize the electrolyte composition as well. So that is something that they left out the detail. And this, I think, is going to be one of their bottleneck points. And this is a paper from the Sil-ion group. So they take this huge particles and then cover it with conductive polymer, and then when you lithiate it, the silicon expands, but it also breaks apart. But because this polymer, it's like a rubber band, it keeps everything together. It's like a 3D rubber band, and it keeps everything together, and it doesn't lead to loss of active material through solid electrolyte interface. So if when you discharge it, the particle still retains morphological shape. You see silicon and CP, conductive polyacrylonitrile, and this is silicon. They claim that even after cycling, it retains the structural integrity. So they show some graphs. This is their custom electrolyte, using conventional electrolyte. They're looking at 60% capacity, that's Coulombic efficiency, specific charge capacity. Even that's pretty good. I mean, it goes from 3,000 to 1,000 after 250 cycles. In comparison, graphite is more like 360, 350. This is almost 1,000. That's pretty good, but it's only 250 cycles. And they have their own electrolyte, which they showed here, and the capacity retention is much higher. Coulombic efficiency is much better, but has it been tested for thousands of cycles will be the challenge, I think. Okay, I had another picture. I think I missed it out, but this is the approach I believe they're taking silicon particles, cover it with conductive polyacrylonitrile or some other polymer, something similar, and it doesn't break apart, and most importantly, they can bring the cost down to $1.2. That's amazing.
Yeah, this is you think this is where they're starting to implement Sil-ion, the company that they acquired out of Colorado?
Exactly. So this is the, if you look at this graph, this is the Sil-ion work. Ashley Haste wrote this paper, and they talked about how they can do this, but there's a lot more work to be done, I believe, because optimizing the electrolyte and getting it to work for thousands of cycles is going to be a little bit challenging. And optimizing electrolyte on a lab scale is okay, but can you produce that kind of electrolyte in tons and tons of quantity and have it ready, have the supply chain ready, and get the right kind of silicon, get the right kind of polymer coating? So there is a little bit of initial hump where they have to invest into tooling of these these equipments have to make these particles in large scale, and then there has to be another series of equipment to coat these things, and then prepare anode negative electrode properly, make sure it binds to the current collector, it doesn't cause problems, and then there is a proper solid electrolyte interface, optimize the electrolyte, get the right kind of solid electrolyte interface, get the cycle life ready. So this is going to be a massive challenge. I think, as we said, DBE, they're still in revision 4. by the time they finish, probably it'll be like revision 8 or 7 or 8, and then get the supply chain ready, get the silicon anode working for thousands of cycles. So these are the bottleneck limiting points that I see if they really have to scale up. So that's why I believe they said 3 years, it could be 4 years, but the pathways, it's clear, but there are engineering challenges, and some of these are pretty hard engineering challenges. So it's pretty exciting, and I guess that's why Tesla was like, they were saying, hey, if you're really into this kind of stuff, solving hard problems, you should come and work for us, because these are high risk, high payoff problems.
I love it. I think it's super exciting. It does seem like Tesla is trying to partner together and localize a lot of the raw materials that they're using, be it the silicon or maybe it's the lithium piece. I thought it was really fascinating to see their map that they put up of some of these key partnerships that they have with lithium, and they didn't explicitly say where, but I think it's the Thacker Pass lithium that they're going to be using. I want to say it's Lithium Americas who owns that one, and then they had the cathode icon on the map as well that was sort of like central US, and I'm going to take a wild guess and say that that's going to be in Colorado. With the acquisition of Sion, they've got some presence here, but there's also, it's just hotbed of battery engineers that are coming out of CU Boulder. And so I think that there's something in the works there, and then the fact that they've got this map, the fact that they've got the lithium coming out of North Carolina as well. I do believe that that's Piedmont, even though they haven't made an official announcement yet. That's they're for those that watch my videos, they're a sponsor of the channel. I had no clue that was going on, but I started to sense some stuff in the air several days before Battery Day. So I'm really encouraged with what they're doing here, trying to centralize their raw materials as much as possible, shorten the distance that things are traveling, and I think that they're going to replicate this very thing as best as they can on other continents everywhere that they're producing vehicles and have a gigafactory.
Absolutely. I mean, they're absolutely focused on reducing the supply chain limitations. So I wonder where they're going to produce the cathode. I mean, there is another picture. They have a new way of producing this cathode. You need metal sulfate, and I guess some of these sulfates, and there are different grades and then different classes. They need a large amount of, if they want to go from like 200 gigawatt hours to 1 terawatt hour, I mean 3 terawatt hours by 2030, they need lots of these materials. I wonder where they're going to produce the cathode. And there are some discussions in the online forums which about lithium production. For example, let's see, they're going to use some recycled stuff. That's a whole different topic. There's Redwood Materials is coming on board, but I'm not sure. I think they have their own recycling stuff. But let me get this one. I think that I thought was pretty interesting. Lithium. So lithium clays. There is some. No, this is all Tesla cathode. Okay, lithium clay. I believe it's going to be. It's not as simple. They may need to do some optimization, because getting lithium from these clay just by pumping brine water, the salt goes in, picks up lithium, and comes out. Some people say the efficiency is pretty low, and it's not as simple. So there's some discussion around that. So, but the fact that they have enough lithium for the entire U.S. fleet is extremely encouraging.
Absolutely. I'm really excited to see how things unfold, and I'm glad that Tesla is sort of leading the charge here and attacking a lot of these really important problems to get internal combustion engines off the road and replaced with zero emissions. So any final thoughts here? I think we've covered most of everything, but do you have any final thoughts, Ravi?
Well, I'm really excited and hopeful of the future because there is a clear plan in place. It's just a matter of putting the man hours and effort to get it executed. I'm really looking forward to it. I'm maybe being part of this whole action. Just grateful that they're thinking of this scale, thinking of this kind of problems, and getting the funding ready, all of that, putting together the whole piece. What they're doing is just inspiring, and I'm grateful that a company like that exists.
I agree. Well, on that note, I think we'll go ahead and wrap up. Ravi Kempaiah, thank you so much for taking some time here to share your thoughts, and you prepared some great slides that also took some time, so thank you for all of your wonderful preparation work and for sharing your thoughts. Really interesting, and as usual, I'm always excited to hear where the wind takes you and blows you, because I think you've got a really exciting future ahead of you in this industry.
Thank you, Sean. Thank you. I know you've been a great friend, and thanks for having me on. It's always a pleasure, and keep doing these amazing videos. I look forward to the next one.
Thank you. Okay, talk to you soon.